Assalamu alaikum. The glottal flow waveform or the flow glottogram is a representation of the airflow during each glottal cycle. It is derived from the oral airflow signal using inverse filtering, and from this important voice source values can be derived. In this presentation, we'll go through how to estimate the glottal flow waveform from glottal inverse filtering and the relation between the glottal flow waveform and the glottal area waveform. We'll go also through the effect on the voice spectral slopes with examples from Modal, Breathy, and pressed voices. Indirect techniques are used to estimate the glottal flow. Why indirect techniques? Because placing a microphone or an airflow detector directly at the glottic level is invasive. It's more practical to detect the signal at the mouth after it has been filtered by the vocal tract. By filtering, we mean a spectrum of the frequencies from the glottal airflow has passed through the filter, the vocal tract, to produce an output at the mouth after some frequencies has been enhanced and other has been attenuated, some selected frequencies from the given spectrum. And then we use the signal obtained from the mouth and try to inverse the filtering process using the technique of inverse filtering, basically undoing what the vocal tract had did to the glottal signal in order to leave the original glottic signal as pure as possible. Either the acoustic pressure radiated from the mouth or the acoustic flow at the mouth can be inverse filtered to obtain an estimate of the glottal airflow waveform. The upper trace here shows a typical glottal waveform as suggested in the LF model. It demonstrates the airflow in liters per second as it increases and decreases during a vibratory cycle. The lower trace shows the acceleration and the deceleration of the flow, the increase and the decrease of the velocity of the changes in the flow itself. A typical cycle would have three phases, starting with the open phase. In the opening phase here, the airflow starts flowing through the glottis. The glottis is open and the airflow is passing here until it reaches a maximum. During the increase in the flow, there is also a mild increase in the acceleration of the flow. Until this point is reached, when there is maximum flow here, the vocal folds starts to close back again, and this is followed by a decrease in the flow with a more increase in the deceleration compared to the acceleration. Until this point is reached, the maximum dip corresponds to the point of the glottal closure instant. The glottis closed up here. This will be by an abrupt movement of the vocal folds. This will be followed by some flow here, little flow after the glottis has closed, and then the closed phase would start with no flow as the glottis is now closed completely. So these are the main three phases, the opening phases during which the glottis is open with flow and acceleration of the flow. A closing phase, the vocal folds are starting to close back the glottis with decrease in the flow and a more prominent deceleration of the flow until the point of the glottal closure instant, and then it's followed by a return back to the baseline with only a little flow in the start of the in the end of the closing phase before starting the opening phase. These charts here would demonstrate the similarities and the differences between the glottal flow waveform, the bottom trace in here, and the glottal area waveform as registered from an electroglottogram and the second trace in here. You could see the obvious similarities between the two traces as expected. The shape of the flow rate generally follows that of the glottal area opening. As the glottal area increases in size, then the glottal flow would also increase. As it starts decreasing in size, the glottal flow would also decrease. So there are some obvious similarities, but there are also some interesting differences. You could see two of them here, the shift of the peak of the glottal flow to the right in relation to the peak of the glottal area waveform, and this peak in here during the glottal closure, the area stayed at the minimum value, but the flow rate did not stay at the minimum value, but rather has this peak. These differences are mainly related to the acoustic coupling, the interaction between the voice as the source and the vocal tract as the filter. This non-linearity and the relation between the source and the filter can explain some of the differences between the glottal flow and the glottal area. To explore this non-linearity and the relation between the source and the filter, the glottal area waveform reaches a peak earlier than the glottal flow waveform. This is due to the skewing of the glottal flow waveform to the right in here. The cause for this skewing and the delay in reaching the peak is the inertia of the air mass just above the vocal folds during phonation, which causes a delay in the increase in the glottal flow during the opening phase of the glottal area, and also a more rapid decrease in the flow during the closing phase of the glottic area. So this shift to the right is a manifestation of the interaction between the source and the filter and their non-linear relationship. Several parameters can be extracted from the glottal flow waveform, and these parameters can have some clinical implications. Some of these parameters are related to the duration of the phases of the glottal flow waveform. Others are related to the amplitude of parts of the waveform or its time derivative. Starting with the duration related parameters, we've seen that a typical glottal flow waveform is divided into three phases: the closed phase, the opening phase, and the closing phase. Now, the open quotient is the sum of the opening phase and the closing phase divided by the total duration of the cycle. During this part, during the open quotient part, the glottis is open. It's opening here and it's closing here, but there is some flow during these two phases. the sum of these two divided by the total time for the cycle gives the open quotient. The closing quotient is only this part in here, the closing phase divided by the time of the whole of the cycle. There is another parameter here, the skewness quotient. This would refer to the degree of the skewness of the curve, usually to the right. You would have a slower ascent than a more abrupt descent of the flow, and this skewness here can have clinical implications. The skewness is the opening phase divided by the closing phase. So rather than adding them together, we're dividing the opening phase in here by the duration of the closing phase to give the skewness quotient or the speed quotient. This skewness quotient, which is defined by the duration of the acceleration divided by the duration of the flow deceleration, ranges between 1.1, where the two are almost equal, the duration of the acceleration and the duration of the deceleration, to 3.4 when the opening phase is as much as 3 times the duration of the closing phase due to the abrupt closure of the vocal folds. So the physiological range would be these 1.1 to 3.4. A higher value than this would indicate that the flow decreases very rapidly in the closing phase, which will lead to a higher vocal intensity. This is usually related to hyperfunctional dysphonia. The glottal flow skewing to the right is just one of several indicators of a strong source-filter interactions. These interactions would suggest that the relationship between the source and the filter is not linear, rather it's a non-linear with feedback from the filter affecting the source as well. This interaction can happen at least at two levels. The first level is the interaction caused by the vocal tract, the filter pressure on the glottal flow, as we have seen. And the second level is the interaction of the filter, the vocal tract, on the vocal cord tissue movements. So the interaction affects the tissue movement of the vocal folds itself in level 2 and affect the glottal flow in level 1. In glottal flow, there are two examples of them. One is the glottal flow skewing, the delay in the peak of the glottal flow relative to the peak of the glottal area, and the other is the ripple component in the glottal opening phase. We've been through some of the parameters describing the glottal flow waveform related to the duration of some of the phases of the glottal flow waveform. Things like the open quotient, the closing quotient, and the skewing quotient, all related to durations of the phases. There may be some difficulty in the exact identification of the start and the end of the different phases due to some impurities in the estimated signal while inverse filtering it. These impurities would allow some indecisiveness in the identification of the exact moment of the start and the closure. If there is incomplete cancelling of the formants, the effect of the filter on the signal is not completely removed. The exact start and end point of the phases can be difficult to identify. That's why another set of values related to the amplitude rather than the duration of parts of the glottal flow waveform, or its time derivative can be of value. Things like the maximum flow obtained from the glottal flow waveform and the maximum airflow declination ratio obtained from its time derivative. This is a chart of the glottal flow waveform and its time derivative here on the lower tracing. The negative peak of the time derivative of the glottal flow in the closing phase of the flow is much more dominant than its positive peak in here. This is very dominant and clear. The instant of the most negative peak is considered the point of main excitation of the vocal tract. And the corresponding negative peak in here is referred to as the maximum flow declination rate. This is a measure determinant of the peak amplitude of the produced voice. This is a computer-generated diagram of modeling of the different factors that interplay during a vibratory cycle of the glottis, including the glottic area waveform, the glottic flow waveform, and the intraglottic pressure. The glottic area waveform would depend on the smaller of the two entities, the glottic entry or the glottic exit in the glottic canal. So the lower of the two will determine the glottic area. They will be equal, the glottic exit and the glottic entry, at the peak of the glottal area waveform in here, when the configuration of the vocal folds change from convergent to divergent. This would be the peak of the glottal area here. The glottal flow waveform would have a peak that is shifted to the right, skewed to the right in relation to the glottal area waveform, as we have described earlier, due to the vocal tract air inertia. There are other manifestations of the interaction between the source and the filter in the glottal flow, and that there is a rapid declination here of the glottal flow, and there are some ripples at the opening of the glottal flow. All these manifestations plus the shift of the peak to the right are due to the interaction between the glottic signal and the filter, the vocal tract filter. You would also notice that the intraglottal pressure does not reach the zero level when the vocal, with the peak of the glottal area, when the glottic canal is fully open. It actually reaches the zero level at the peak of the glottal flow rather than the peak of the glottal area waveform before going into the negative pressure in the divergent phase of the glottal cycle. The duration of the open phase in relation to the total duration of one vibratory cycle gives the glottal open quotient. This has its effect on the voice source spectral slope. If this ratio lies between 0.4 and 0.7, as in normal voices, if it is less than 0.4, it usually indicates a pressed voice, and if it is more than 0.7, it's associated with a breathy and weak voice. This voice source spectral slope graph comes from the fact that the harmonics produced by the voice source changes as the frequency increases. This rate of change of the harmonics when the frequency increases, gives the spectral slope. The lower harmonics here, the lower frequencies, are affected by the increase in the glottal open quotient. If you have a high glottic open quotient, like more than 0.7, then you would get a higher dominant first harmonic and a breathy and weak voice. And conversely, when the open phase is short, this would cause most of the glottal flow changes to occur within a smaller duration. This leads to energy boosts in the low frequency portion of the source spectrum. The shortening of the open phase would, in contrast, makes the second harmonic or even the fourth harmonic more dominant, and this would give a pressed voice quality. The glottal flow waveform and its time derivative waveform shows clearly the vocal fold closure is much faster than the vocal fold opening. This abrupt vocal fold closure determines the amount of energy in the acoustic spectrum and would show a slowly reducing spectral slope rather than a sharp decrease in the spectral slope. The overall number of the harmonics is also be influenced by this abrupt closure, and the amount of energy in the high frequencies can all be affected by the decrease in the duration of the vocal fold closure. The time taken for the vocal folds during its abrupt closure to close up the glottis is termed TA and can be calculated from the glottal flow chart and its time derivative in this time in there. This period, if it is shortened, if you have a very abrupt closure of the vocal folds, would result in a bright voice which projects well, as we have just seen. On the other hand, if there is incomplete closure of the glottis or slow vocal fold closure resulting from, say, a pathology or paralysis, this would result in less energy in the acoustic spectrum and fewer higher harmonics. This will result in a breathy voice that is not going to project well. By this we come to the end on this presentation on the glottal airflow waveform. Assalamu alaikum.